Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems of the circular current carrying wires. So you can see that in the first case, which is the very basic problem of this magnetism. So in the first case, you can see that there is an infinitely long wire which is carrying a current I from infinity, and this wire is connected to a semicircle which is carrying this same current and forwarding it to the another infinitely long wire. So we have to find out the magnetic field at this point O, which is the center of this system. First of all, let us talk about the directions of magnetic field. We have already discussed previously in the section of straight wires that if this is a wire, let us draw the wire. So this is a wire which is of infinite length, and this point is O, and it is carrying a current I like that. So this wire creates a magnetic field in the downward direction at this point, which can be seen by Fleming's right hand screw rule. Okay, you can use the right hand screw rule and you can find out the direction of magnetic field. Again, if I talk about the upper wire, so this is the upper wire, this one, and if I talk about the upper wire, so the upper wire is also taking this current in the backward direction towards infinity, and point O is on the downside of the upper wire, and the magnetic field of this upper wire will be again inside the plane of the screen at point O. Okay, so and obviously the magnetic field of this circular arc will be also inside the plane. So the magnetic field due to all of them will be inside the plane, and we can easily find out the magnetic field by adding up the magnetic field of each one of them. Okay, first of all, we have calculated the direction separately for each wire, but now if current is following a cyclic path, you can see that this current is moving in a cyclic path around this point. So the point which is bounded between a cyclic path of the current will have the magnetic field in the same direction by all of the parts of the cycle, and you can find out that direction by using your Fleming's right hand screw rule for circular rings. So for example, if this was a ring, then current would be flowing in clockwise sense, and if you rotate the fingers of your right hand in clockwise sense, then you can see that your thumb would be pointing in the downward direction, and hence we can say that the magnetic field at the point O will be pointing inside the plane of the screen. So we can directly find out the magnetic field at point O. So now let us first of all find out the magnetic field due to this single wire. So due to this single wire, we can see that one angle is 90, because from one side this wire is going to infinity, and the other angle is 0 degree. So B will be equal to mu naught I by 4 pi A. Now A is R, which is the perpendicular distance, this is R, and sine 90 is 1, sine 0 is 0, so this will be the magnetic field. And this is, let us name the wires as wire 1, this is wire 2, and this is wire 3. So this magnetic field is due to wire 1 and 3, so we can write down that B1 and B3 will be equal to mu naught I by 4 pi R. And B2 is the magnetic field due to this circular arc. So B2 will be equal to mu naught I by, we know that for full complete circular wire, B was mu naught I by 2R. Now for this semicircular wire, B will be mu naught I by 4R. And the direction of all of them is same. So we can just add up to find out the net magnetic field. So B net will be equal to mu naught I by 4R plus twice of this. So it would be mu naught I by 2 pi R. So this will be mu naught I by 2R, and it would be 1 by 2 plus 1 by pi. Yes. Okay, so this will be the net magnetic field due to this system at the point O. Now you can take the screenshot of this one, and I would be removing this part, or what we can do, we can just use another page for this problem. So let us use this problem on the next page. Yeah, so you can see that this is the one second. Yeah, so in this case you can see that again the current is following this cyclic order, and this point is bounded between this cycle. So we can say that the magnetic field will be in the direction which is governed by Fleming's right hand screw rule. And if you can imagine a ring in which current is moving like that, which is in clockwise sense, then the magnetic field at point O will be in the plane of the screen. So we can say that the magnetic field due to all of the three wires, first one is this straight wire, second is this, third one is this, will be same. It will be in the same direction, and hence we can add up all of them. So B1 will be equal to mu naught I by 4 pi r, and one angle is 0 and one angle is 90, so it would be sine 90, and direction will be inwards, and B3 will be same, equal to B1, so it would be mu naught I by 4 pi r. And B2 will be equal to mu naught I by 2r, and you can see that this is a quarter ring, and the quarter ring is making an angle of 90 degree at the center, and therefore we can multiply it with pi by 2 divided by 2 pi. So directly we can also multiply the complete magnetic field with 1 by 4. So B2 will be equal to mu naught I by 8r. Direction is also inside the plane of the screen. So now B net magnetic field will be sum of all of them. So it would be equal to mu naught I by 2 pi r plus mu naught I by 8r. So it would be mu naught I by 2r, and this is 1 by pi plus 1 by 4, and the direction will be inside the plane. Okay, now let us move on the next problem. You can see that in this problem, the first one, there is an infinitely long wire which is carrying a current like that. This current is moving in a partially circular arc, and it is going to infinity like that, and we have to find out the magnetic field at the point O. Now again we cannot say that. Now you can imagine that if this wire is taking this current like that, and suddenly there is a discontinuous point where slope are different and current is moving like that, so we cannot say that this is a uniform cyclic order. So we cannot say that the magnetic field will be same due to all of the three wires. In fact, let us see the magnetic field direction. I was only talking about the direction, same in the direction, okay, not in magnitude obviously. So if I'll talk about the magnetic field due to this first wire is this one, and the second one is this one, third one is this one. So due to the first wire, if this point is this one, we have to extend the wire and we have to draw a perpendicular. So like that, it would be the perpendicular, and this perpendicular will be r cos 30. Okay, and r cos 30 will be equal to root 3 r by 2. This angle is 30. So A is equal to root 3 r by 2, and if we join this point with this end, and if we join the other end of the wire like that, so you can see that this angle will be 30 and this angle will be 90. And if you remember the special case, that if this point is lying on one side of both ends, then the B was equal to mu naught I by 4 pi A sine phi 1 minus sine phi 2. We have already discussed this special case previously. Let us use the next page. Yes. Okay, yeah. So B will be equal to mu naught I by 4 pi A is, let us write it down on the next line. B will be mu naught I by 4 pi A. Now A is root 3 r by 2, and if you are not remembering that which one is phi 1 and which one is phi 2, we can easily say that phi 1 would be the greater angle, because we are just calculating the magnitude of magnetic field and it cannot be negative. So we have to write down the greater angle sine minus smaller angle sine. So greater angle is 90, so it would be sine 90, and the smaller one is 30, so it would be sine 30, and B will be equal to mu naught I by 4 root 3 pi r. What I've done, I've written it as 1 minus 1 by 2 is 1 by 2, and cancelled that 2 with this 2, and this would be 4 root 3 pi r. So this is only the magnetic field due to the wire 1, B1. Okay, and it would be the same magnetic field due to wire 3, so it is also equal to B3. And to calculate the magnetic field due to 2, we can use the formula of partial ring. So it would be mu naught I by 2r, and you should always remember that alpha upon 2 pi in that formula, alpha was the angle which is subtended by that part of the ring which is carrying the current. So in this case, the ring which is carrying the current, the part of the ring which is carrying the current, is making an angle of 300 degree at the center. So into 300 divided by total angle 2 pi in degrees will be 360. So this will be the 5 and this will be 6. So B2 will be equal to mu naught I, 5 mu naught I, or 1 second. B2 will be equal to 5 mu naught I by 12r, and B net will be equal to sum of all these three magnetic fields. So it would be mu naught I by 2 root 3 pi r plus 5 mu naught I by 12r. And the direction, in fact, we have to check the direction first of all. We know that the direction due to this wire and this wire is same, so we would be adding these two. So by adding these two directions, we can see that we can just make it twice. So this will be the result, and the magnetic field direction due to the ring is inside the plane. You can see that this magnetic field will be in outside the direction. You can use your right hand screw rule and find out the direction due to the magnetic direction due to this straight wire, and again you can use your right hand screw rule to find out the direction due to this arc. So due to this arc, if you curl your fingers of the right hand in the sense of rotation of current in the arc, then you would see that your thumb would be pointing in the downward direction inside the screen. So we can say that the magnetic field due to this ring will be inside the plane. Okay, and we can also predict that obviously B2 is greater than this B. So let us use a negative sign here and positive sign here. 5 by 12 mu naught I by R, and the net magnetic field will be in the direction of the greater magnetic field. So the greater magnetic field is cross, so the net magnetic field will be in the cross direction. Okay, now let us move on this problem. In this problem you can see that these wires are again taking the current like that, and it is going in a ring, and this wire is taking the current to infinity. Now again, if we see the direction first of all, then we can see that the direction due to all of these three wires will be same, and it would be it would be inside the plane of this screen. And to find out the magnetic field of this wire, straight wire B1, let us extend this wire and let us draw a normal. Okay, so this is 30 and this is 60, and this is R, so it would be R cos 60. This is R by 2. So we can say that again this is the case in which the point is on the same side of this perpendicular. If you draw a perpendicular, wire is this one, and this is the perpendicular, and this point and this point are on the same side of the perpendicular. So the B formula of magnetic field due to the straight wire in this case will be mu naught I by 4 pi A. Now A will be this one, R cos 60, which is R by 2, and sine bigger angle, one angle is 90, and the smaller angle is 60, so sine 60, and the direction will be in the inward direction. So B will be equal to mu naught I by 2 pi R, sine 90 is 1 and sine 60 is root 3 by 2. Direction is inward. This is B1, and B1 will be equal to B3, and B2 will be the magnetic field due to this arc, and magnetic field due to the arc will be again mu naught I by 2R. The angle subtended by the arc at the center, current carrying arc at the center, is 300 degree, and the total angle is 360 degree. So B2 will be equal to mu naught, this is 5 mu naught I by 12R. So B net will be equal to twice of B1 plus B2, and twice of B1 will be mu naught I by pi R, 2 pi R, 2 minus root 3, plus 5 by 12 mu naught I by 12R. In fact, we have already written this 12. Okay, so this will be the answer of this question. Okay, now in next video we are going to discuss level 2 problems of the current carrying wires. Thank you.